Alright folks, I'm going to look at some new rules in this video, next couple videos. Kind of got them grouped together in terms of notes and things that I've shared with you, but what we're going to focus on, so we're looking at product and quotient rules, and we're going to focus on the product rule in this one. This slide kind of, full disclosure, I start off with one huge slide show, and I broke it up into two. So we got two additional rules, just one for this video, the other one will be a next video. But the idea is that these are built up from functions that are kind of smaller functions. So it's kind of like the sum and difference rule that we had before. So you might know that f and g are differentiable, and think about the ways that you can combine them. So just as a reminder, you might have f plus g. That would be a way to create a new function, f minus g. And so then if you're going to look at the derivative, you got the sum rule that we talked about, the difference rule. What are some other operations that you can use to create new functions? We can multiply them together, which we write like that, just with the juxtaposition typically. You could divide them. You could compose them. Again, that open circle there, it's not a really small zero. It means that f composed with g, so kind of treat g as the input for f, and however you think about that. So we've got this one from previous work, we've got this one from previous work. Here we're multiplying two things together or looking at the product. And that's what we're looking at in this video. So this one will be the next one, and this one will be a little bit down the road with the composition. So, product rule. Like I said, we're going to use the product rule when the function we want to differentiate, if we see it as the product of two functions, and not just any two functions, but two functions that whose derivatives we know. I'll show you what I mean in just a second. So for example, if you had f of x equals this quadratic times this linear function, you can view f of x as the product of those two smaller, so to speak, functions. Now what you could do in this case to avoid it is you could just say, well, let's expand, and we say 3x cubed plus 5x squared plus 6x squared plus 10x minus 12x minus 20. And then you've got a polynomial and you don't need this new rule. But we're going to see plenty of functions where you have to use this rule. So I'm going to go ahead and discourage that, something like that for this problem, even though, in this case maybe it is easier to just expand it. So thinking about what this rule might be, remember, for if f and g were differentiable, it works super nice if you're just adding the functions, you're looking at the sum. It is a little bit more complicated and not so clean with the product rule. So if you're thinking about it like this, you might guess, it would be perfectly reasonable to guess that that's the formula for the product, the derivative of the product of two functions. And the problem is that is incorrect. So a natural, reasonable guess, but it is wrong. That is not the formula. Just a real quick, silly example. Suppose we've got y equals x to the sixth. Now, reasonable people would never do this, but you could write it as x to the fourth times x squared. Now you see it as a product of two things. You already know how to do the derivative of this, and we're going to use that fact, but you know how to take the derivative of these two factor functions anyway. So derivative of x to the fourth by the power rule is 4x cubed. Derivative of x squared is 2x. So if we were to look at the product of these two, this times this, you would end up with 8x to the fourth. So if we had guessed that this formula worked, look at the product of those derivatives, we'd end up with 8x to the fourth. But we already know for sure that the derivative of x to the 6th is 6x to the 5th. So this derivative has to be 6x to the 5th. Can't be that. So what this does is show us that our proposed rule cannot be correct. And it is not correct. We got one example where it fails. That's enough to say that it's not true. So here's the real product rule, the correct one. And boxed in here for you, or if you like, in that notation. So if f and g are differentiable, the function created by their product, f times g, is also going to be differentiable, and that's going to be defined in this way. So when I think of these as product, I usually think first and second function. If you like, left and right function, however you want to call it. You know, it doesn't have to be f and g, but you'll have one that's kind of a first and one that's a second, if you like. The way I think of it is I take the derivative of the first times the second, plus the first times the derivative of the second. And, you know, thinking about it with the prime notation maybe is a little bit easier. F prime times g plus f times g prime. The textbook that we use for this course has this shuffled up a little bit with how it's written, but I find it easier for me to keep track of it this way, so that's how I'm presenting it here. So very much a different formula than what we might have guessed, but this is the correct formula. We can prove it, but we're not gonna worry about that. We're just worried about, you know, getting this figured out and being solid with it. So we can look back at that example. I think that was the example. It wasn't, but that's okay. Same type of example. Suppose we want to compute the derivative of this. Now, again, we could expand this, and then we would just have a polynomial, which we know how to handle, but let's play the game and just use the product rule. So if we did that, we can see this as the blue function as the first, red is the second. Take the derivative of this times that, and the first times the derivative of the second. These derivatives are, relatively speaking, pretty easy, very manageable. 2x there plus 2, and that's that constant, the derivative of that is 0, so I get 2x plus 2. For this one, constant, the derivative is 0. Derivative of this would be negative 14x. And a way to check would be to expand f of x first, what we had up here, differentiate, then compare with this expanded. And it will work out the same. It's just kind of, you know, extra practice with algebra, arithmetic, and all that stuff. So we're not going to do it here, but it will work out the same. We could do that same thing here. We could have just multiplied everything out. We've got 9 terms initially, maybe some things combined. It starts to get to be a little bit tedious. So I'm going to avoid doing that. But I will write this out. So if I want to do f prime, it's going to be, I'll take the derivative of this, which is 2x plus 8 times x minus 3x squared plus x to the 4th. That's just the second function. Now it's plus the first function times the derivative of the second function, which would be 1 minus 6x plus 4x cubed. One way I could check my work is that if I look at the leading term, x to the 4th leading term here, when I multiply everything out, I would have an x to the 6th. If I look at that here, I would have a 2x to the 5th. Here I would have had a 4x to the 5th. That would combine to give me 6x to the 5th, which is the derivative of x to the 6th. So I can kind of maybe see that if I expand everything out, it works. But this is perfectly fine here to leave as an answer. Some folks get worried about the, simplifying, whatever that means. If you're going to, quote, simplify this by combining all the like terms, there's not really a lot there. You basically have to expand it and group things together. If you're going to do that, you might as well do it in the first place, and then you don't have to use the product rule. So something like this, perfectly fine as an answer. For this one, when we talked about this, when we introduced the power rule, we had to distribute that t squared. There's no way around it. So we would have said t to the 5/2 minus t cubed. Power rule, and you're in business. But we can use the product rule here. I could take the derivative of the first, 2t times the second plus the first times the derivative of the second and maybe with a little bit of practice we're starting to get the hang of that. Remember what the derivative of the square root of t is, or square root of x, whatever it might be. 1 over 2 times the square root of the variable. So this one, the derivative is pretty clean. It's just 5 halves t to the 3 halves minus 3t squared. If you were to expand everything out and group things together, you would get the same thing. So both of the second one, I would say definitely faster to expand and then do the derivative, but it's just to show you that these formulas work. So there's what it looks like, and I think that's what I wrote. Looks like what I wrote. All right. So that's our rule for when we have a new function that we can view as the product of two functions that we know how to handle. And again, we know how to handle this one. We know how to handle this one. So product rule makes sense to try. Again, maybe faster to distribute. We'll leave that aside. What we'll look at next is how we can handle a function that we see as the quotient of two functions, which means one divided by the other. And that'll be the quotient rule. It's like the product rule in the sense of it's probably not what you first think it might be. It's a little bit more complicated, but pretty similar structure to the product rule. So we'll look at that one in an upcoming video.